and welcome to Enough with the Science. I'm Joe.
And I am Senan, and this week we're waving at you joyously.
We better explain what we do here, because some people might have stumbled in here by mistake. So welcome to our little podcast. Essentially, Senan is a science nut. Nerd. Maybe nut is better. And
Which kind of nut? Would it be walnut or almond or hazelnut?
No, bigger than
maybe?
that. Much bigger than that. And so basically, Senan likes to explain the fundamental nature of the universe works. And we try and understand it, and I try and derail his plans as best I can with innuendo and folly.
And when you think about it, right, that means the universe is trying to explain how it works.
To itself.
To itself.
So depending on how intelligent or stupid the universe is, this will be a very successful podcast.
But I guess like a lot of things in the universe, there's a range, isn't there, of brightness versus dimness.
Yes, it's all in a climb.
Just like there is with light.
Ah, look at that. You finally got a segue right. This one is a bit of a head melter now. Here we go.
Yeah,
right.
We're going to do something this week that is different. At least we've never done it before.
Yeah.
And
this is light entertainment.
Oh. Look,
there we go.
I'm not at the races. So we're going to do a two-parter. See, we're here to talk this week about the waves that underpin much of the universe. And strictly speaking, it's called electromagnetic radiation. I'm going to call it EM waves from now on.
Okay. I bet you won't, though. I bet you'll say.
I'm saying electromagnetic radiation 100 times in the next half an hour.
I bet you'll forget. I bet you won't. You'll forget EM waves. That's never going to happen.
Anyway, so light, of course, is one of the things that is part of this wonderful world of EM waves. See, I remembered.
I'll note it down.
So we're talking about that, and it's a two-parter because there's just so much material, and we're gonna talk about some of the.
This is how much we respect you. This is about respecting the listener.
Yeah, no, it's about basically wringing every last minute of recordable podcast out of every subject you can think of.
We may return to this next season.
Yeah, or even it might turn out to be a three-parter. Who knows?
Or maybe it turn out to be the last one ever.
Yeah, it could, but anyway, we're talking about EM radiation or EM waves, of which there are many different flavors, and that's part of what makes it so interesting. That this one thing comes in so many different flavors with different properties. But I guess the first thing to talk about is, where does it all come from?
Well, that's a good start.
Or what is it? So it all starts with tiny charged particles, electrons usually, and they wiggle, or that's a fancy way of saying they either accelerate or they change direction. And anytime an electron accelerates or changes direction...
Is that what wiggle means?
I've just made it mean that.
Okay, that's what it means here. Okay.
Here for the subject, in the context of this little podcastino of ours. Anyway, there is a thing fundamental to the entire fabric of the universe called the electromagnetic field. It permeates everything, the vacuum of space, the matter that we're made from, the floor underneath us.
Yeah, I do love the fact, though, that essentially we're standing in a field. It's
We
all
are.
down to being
We're
in
all
this
farmers.
field. We are all standing in our own field.
Yeah, we're all outstanding in our own field. Well, some outstanding more than others, Joe.
Well, this is going to be an outstanding electromagnetic radiation field.
So this thing that we can't see or feel, this electromagnetic field that permeates the entire universe, is everywhere. But so the properties of this field essentially allow matter to stick together. So, nothing that we recognize as ourselves or the objects around us would actually exist without this field, because it gives properties to the way it interacts with the ordinary matter.
Okay, now I'm just going to throw a complete spanner in the works. Is this a theoretical construct so that we can understand how things work on a subatomic level?
I don't know.
Good. And next week, no, we'll be looking at whether this is theoretical or not. No, because I'm imagining that there's this. I'm trying to physically imagine an electromagnetic radiation field that goes everywhere in the universe, and that all of these things are flowing through. But maybe I'm just wasting my time.
I believe theoretical physicists can infer it because of all of the rules about the way the universe works that they have developed over time.
Okay.
So they can, if it doesn't exist, none of the stuff they've discovered makes sense. Or a lot of the stuff they've discovered doesn't make sense.
When I was in science in school, I would be kind of going, maybe it doesn't exist.
Anyway, so an electron accelerates or changes direction. It creates a ripple in this field, and that ripple spreads out as a wave. And that's essentially what EM radiation is, right? That's the end of the show.
Okay, that's it. I kind of understood it. I kind of understood that. So the electron are the tiny little bits of atoms that rotate around atoms.
Yeah.
And they either change direction or speed.
Yeah.
And this creates ripples.
In the electromagnetic field, yeah.
Okay.
Yeah. But the wave carries energy with it. We're going to come back to that in a minute.
Okay.
These waves are regarded as self-propagating. Now, what do I mean about that? You know, the waves that, if you go down to the beach and look at the waves in the sea, they couldn't exist without the water. Those waves require the water as a medium to travel through. And similarly, you can hear the rubbish coming out of my mouth right now, and you would not be able to hear that was it not for the existence of air in the room around us. So the waves of
Wait
sound...
a minute. You're telling me if I remove the air?
Yes.
Let me just write that down.
Go ahead and remove the air, Joe. See what happens.
Hold on. We have a solution. Rather drastic.
But so the sound waves required air to propagate. They require a medium to travel through. And indeed, they could travel through water also. Radio waves, EM waves, do not require anything to travel through. So they travel perfectly well through vacuum of space where there's practically no material. And that's why it's called self-propagating. But even weirder than that, and the weirdness is going to go fairly off the scale this week.
That's weird enough. That is weird enough. I'm just going to lie down.
There's actually two waves involved. So it's called an electromagnetic radiation because there's an electric wave and a magnetic wave, and they're traveling at right angles to each other.
Ouch.
Very hard to visualize that, but imagine you're standing at the sea again, and
Okay.
you're looking at the waves coming in the beach. You know, the peak of every wave points up towards the sky, and the trough of every wave points down towards the seabed. So they're straight up and down, as it were. Now imagine there's a second wave traveling with that, and its peak is pointing to the left and its troughs are pointing to the right. So it's like a cross, if you like, traveling through. If you were to look at a cross section of EM radiation or EM waves, it would look like a cross traveling through space. And things start to get even weirder.
But because to imagine that, you have to kind of imagine that it's on a plane, like kind of a flat, to see a wave traveling through something, whereas they're going all directions at once.
Well, yeah, I mean, so you switch on say you light a match.
Okay, good. Now, that's my level. Back to my level now. I understand that, a match. Good.
Yeah. And instantly, no matter what side of that match you're standing on, if there's 10 people in the room all standing around, they will all see roughly the same amount of light coming out of that match. So what's happening there is that waves are going off in all directions. It's not like that that one wave is spreading out into a wide cone all over the place. It's that there's billions of individual waves emanating from that flame and going off in all different directions.
Okay.
So the light that hits your eyes is a different wave to the light that hits the guy standing beside you. You know, so that's kind of what I forgot. How did we get into this?
No, you were just explaining how how the electromagnetic waves are traveling through the universe, but they're traveling in all directions.
Yes.
They're just not on one plane like a wave, like you see at the sea, and it's not like a cross coming through the sea. It's because it's going in all directions, up and down, around and backwards.
And true. My analogy of the sea does break down there because the sea is essentially a two-dimensional surface, whereas obviously space is three-dimensional, or more dimensions, depending on if you're studying.
Let's not go there. Let's not go there. There's another episode.
So how do these things actually get generated? Well, for radio, for example, radio waves, there's the transmitter has an antenna, like a little metal pole thing, and electrons are bouncing up and down inside that antenna. And every time an electron comes to the top of the antenna, bounces off the top of it and starts heading back down again, that change of direction is what generates the radio waves that are emanating out of that antenna. So that's radio.
So if we were doing this 20 years ago, that would be how you were listening to us, but it's probably not now.
It's probably not now, no, but you never know. Maybe we'll make it big someday and we'll find ourselves on the BBC.
Well, yeah, they can't afford us. They could afford us.
They can't afford the blasphemy that we utter, that's for sure. So, That's radio waves. Then there's another example of how EM radiation gets created is in a light bulb, or indeed in a star, and the nearest star to us, we call it the sun.
Well, you just go scale, don't you? You just go in a light bulb or a star. Let's go the opposite end.
Yeah.
Let's go. Yeah.
Why not?
Nothing in between, not like kind of light bulb, street light,
Yeah.
front of a plane.
Yep. Well, look, imagine whatever light source you want.
Yeah.
So electrons jump between energy levels. Now, this is something we've touched on before in other contexts, but what are we talking about, right? So electrons are orbiting around the nucleus of atoms, and they're kind of in what are known as shells, which are like, if you imagine several concentric circles, a small circle in the middle, then a slightly bigger one, then a bigger one, and a bigger one.
So like kind of Russian doll atoms.
Yeah. Imagine if you cut a Russian doll in half and look down at what the cross section.
You're very violent. Could you not just imagine a full Russian doll with all the bits inside it? We can do that. We can go that far without having to like chop it.
I suppose we can. I grant you that.
Yes.
I'll put my chainsaw away.
Okay.
So if you want to make one of those electrons jump from, say, an outer shell into one of the inner shells, you basically have to give it more energy. And there's like a specific amount of energy that you have to typically give an electron to make it go into the next shell.
So you have to do something.
Typically something interacts with that molecule. So, might be strong radiation coming in from outside and hitting it. It might be a chemical process. It might be in the process of reacting with some other chemical. You could be talking about fusion in the core of a star where everything is getting squashed together. All kinds of things could cause it. But essentially, we're talking about an acceleration of an electron from one shell to another. So that movement will also generate EM radiation. Or probably the best example of all is absolutely everything you can see right now, including yourself, is generating infrared radiation. Because any object which is warmer than absolute zero, which is about minus 270 Celsius.
That's a lot of objects.
Is releasing some heat. That's most of the objects in the universe. Is releasing some heat. Anything warmer than absolute zero there's infrared radiation just leaking off the surface of it.
So ice is making heat. Ice is creating heat.
Yeah, ice, which is like 273 degrees warmer than absolute zero, is actually there's heat emanating from it. But there's less heat emanating from it than you or me.
Yeah. Or than the drink you put it in.
Yeah. So that's what's going on there is the heat of an object is determined by how much its molecules are vibrating. So if you cool something down to absolute zero, what you're essentially doing is stopping its molecules from vibrating. And the warmer it gets, then the stronger the vibration is, and that vibration, that movement over and back of the molecules, that actually generates EM radiation in what we call the infrared band, and we can actually obviously our eyes can detect visible light, but we can also detect infrared radiation, because if you put your hand like a couple of inches away from a hot pot, you'll feel heat in the air, and that's actually
so heat is essentially infrared light.
Yeah, pretty much. Yeah. So heat that we feel propagating through space is infrared light. The actual heat of the object itself is the vibrating molecules in it.
Okay.
And then you've got another thing called convection. So where heat exists in a place where there's a gas like air. Heated gas rubs off that object, gets heated up, and then rises because it's less dense than the gas which hasn't been heated up. So that's another way that heat gets spread out. But yeah, broadly speaking, what we experience as heat is infrared radiation. Yeah. There's a couple of technical nerdy measurements we need to talk about, because they'll help us.
Do we have to?
They'll help us understand a bit more about how all this stuff works. And especially, as I said at the start, you've got all these, we're talking about everything from radio waves up to gamma rays, and a lot of other things in between, like microwaves and infrared and X-rays and so on. And they're all made of the same stuff, this electromagnetic radiation. And the only thing that separates one kind of EM radiation, oh my God, I said the entire thing a moment ago.
Very good. I knew you would. I knew you wouldn't be able to keep to it.
And is these measurements of frequency is the first one. Now, frequency is how many waves pass you by. So,
My life is passing me by.
yeah, at a great frequency.
One life at the speed of one life.
So imagine you're standing still and there's a wave going past you. The frequency is how many of those waves pass you every second. And another word for it is hertz. So if a wave is traveling at 1 hertz, it's 1 wave per second passing you by. So you'll often hear megahertz, which would be millions of hertz. So that'll be millions of waves per second, or kilohertz, thousands of hertz, thousands of waves per second. So that's frequency. Then you've got wavelength, which is literally the length of one wave from the peak at the start right down through the trough and back up to the peak that is just about to start another wave. And the interesting thing is frequency and wavelength are related to each other. So as the frequency goes up, as the frequency gets higher, the wavelength reduces. So you get some, like radio waves, some of them can be kilometers long. And then say gamma radiation, which is at the other end of the spectrum in terms of strength, you're talking about umpteen billions of them able to fit into 1 millimeter. So like it's a huge difference.
It's a big range.
Yeah, it's a big range.
The kind of the classification though is kind of arbitrary, is it? If you know,
you mean visible light or infrared or gamma or X-ray? Yeah, like that's just convenient for us.
Yeah.
We based on the behavior that the different kinds of waves exhibit, we divide them up into these categories that are just human. And the reality is, right, if you go to the boundary, we'll say, between visible light and infrared light, you know, slightly one side of the boundary versus slightly the other side of the boundary, you won't notice a whole lot of difference between those two. Yeah. So it's not like that there's a sudden change, like walking down a step on a stairs, you know, when you move from one part of the...
So could you like kind of just research one particular little tiny frequency or wavelength and then just name it Senin? Senin rays.
Senin's band.
Senin rays.
Yeah. I always wanted to be in a band, you know.
Just those little ones.
And you know, it shouldn't really matter that I haven't a single scintilla of musical knowledge. And
that has completely toned deaf. There are many people who've been in bands that like kind of that is not a disqualification.
Right. No, I think I'll stick with the science, even though there might be more than enough. The other measurement that we should briefly talk about is amplitude, and that is how tall is the wave. I'm not going to talk about it a lot other than in the context of radio. We can use amplitude as a way to encode information in a radio signal. Come back to that probably next week. Okay, the weirdness is only getting started, so you might want to. We are
well within. We drove past weird at least 10 minutes ago.
I think now might be a good time to put on your tinfoil hat.
Yeah, I'm keeping that for Christmas.
So there's a thing called photons, and they are discrete packets of energy that are in EM radiation. And in fact,
okay, wait. EM radiation is a wave.
Yeah, so we're talking about wave-particle duality here. It's, for me anyway, one of the most mind-bending things in physics.
just like, there was a story, I think it was Bill Burr told a story about shooting up, he was working for, and someone gave him a gun. This is obviously in America, but someone gave him a really high-caliber handgun and said, why don't we come outside and shoot up this car that's at the end of my yard? And he thought that once he fired the gun that he would like hear a really big noise, but after he finished firing the gun and he fired off 3 or 4 shots, he didn't hear anything except boo in his head. That's all he remembered for about 2 days afterwards. Now I am hearing that noise now. So that is the noise in my head right now.
You're going to have to explain that one a bit further.
Well, it's a particle, but it's a wave. But it's not, the particles are not part of the wave. The particles are the wave, and the wave is the particle, and they're both the same thing at the same time.
Oh my God.
And
you've just clarified it for me.
There you go.
That is the best explanation of wave-particle duality I've ever heard. That's it. Clearly the roles are going to reverse here now. I'm going to do a terrible job of being the funny man.
That cannot be the way things work.
Yeah, it's really peculiar. They've done experiments that prove, one particular experiment that proves it's a wave. Light is a wave, and another different experiment that proves light is in discrete particles. discrete packets of energy.
Indiscrete particles. Like they tell stories.
Lack of discreteness.
Light is indiscrete.
So,
okay, but so these experiments, they're like fundamentally showing that they're different things at the same time.
Yeah. And the reality is that science doesn't really truly understand what's going on there. They can demonstrate with these experiments that light is both a pair of waves and individual particles at the same time. And it obviously, intuitively to us, that makes no sense whatsoever.
Yeah.
And there's a theory, there's several theories, but the leading one that most physicists kind of lean towards, that makes sense, is something called the Copenhagen theory.
Okay.
And I
I'm
think
bracing
that's
myself.
probably because they were well into their third barrel of Carlsberg.
Yes.
So
Then all the best theories come.
Heineken or Carlsberg. I can never remember which one of them is from
Copenhagen, I think, is Carlsberg.
Is okay. Well, I apologise to
yeah,
Heineken if I've
yeah.
gotten that wrong.
Or maybe it's Amsterdam. I don't know, actually.
Yeah.
Some beer. Oh, and this podcast is kindly sponsored by Heineken or Carlsberg, whoever gives us more beer.
Now, interestingly, the marketing wheeze for that is probably, which does apply in this case, because this theory is probably right.
We'll go with Carlsberg. I think Carlsberg fits this much better.
So it's essentially the idea that the wave is a kind of an unresolved probability. In other words, a fuzziness about exactly what condition the energy of the light is in at any point in time.
I have a fuzziness about what condition I am in right now. There's a fuzziness in my brain.
And the probability is only resolved, as it were, into a specific particle when we measure that light. So when the light lands on a surface, we're effectively measuring it at that point. So it's saying that the probability of where exactly the light might be on this theoretical curve of a wave is only resolved when it actually hits something. And prior to that, it's not in any one specific place. It's kind of just probably in a couple of different places.
Okay, so it's a wave until we look at it.
Yeah.
And then when we look at it, it changes into a particle.
That's basically what the theory is saying. So I actually think...
If we just close our eyes.
I actually think we'd have been better off without the Copenhagen explanation.
I think life was much easier then.
It's less mind-bending.
Yeah. So if we weren't here to observe it, then it would all be waves. Everything would be waves.
Yeah.
But because we're here, we have forced it to be a discrete particle.
Yeah. It's like that.
Just by looking at it.
It's like that one about, if a tree falls in the forest and nobody's there to hear it.
Yeah, does nobody care?
Did it ever fall?
Yeah. Does it make a sound? That's what it is. Does it make a sound? Yes, does it make a sound?
As usual, I got it wrong.
You've invented a new one. If no one has seen the tree falling, does it actually, like you might see the evidence afterwards, yes, does it make a sound?
Yeah, maybe the tree was just born on the ground, who knows?
Yeah. But so that's mental. That's just mental that we are changing the fundamental nature of
it's not
electromagnetic.
Proven. It's not proven, but the mathematics points in that direction, shall we say.
I knew it. I knew it was the maths. Never trust the maths.
Yeah. So the interesting thing is essentially a photon is a packet of energy. And the higher the frequency of the EM radiation, so radio waves obviously are at the lowest level, visible light is somewhere in the middle in terms of the frequency, and then X-rays and gamma rays are like really high frequency. So the higher the frequency, the more energy each individual photon is packing, as it were.
Okay.
And you're talking about, once you get up to X-rays and gamma rays, you're talking about absolutely ridiculous amounts of energy in one tiny little packet, and can do ferocious damage when it hits things. So anyway, a direct relationship between frequency and energy of the photon, and an indirect relationship between frequency and the wavelength. In other words, when frequency gets higher, wavelength gets smaller, and vice versa.
Well, it's almost like mathematics. I didn't think my head could hurt anymore. Just to go back, so at the higher levels of the wavelengths, or the photons have more energy.
Yep.
And photons get their energy...
Not at higher wavelengths, higher frequencies.
Higher frequencies.
Yeah.
So the photons then, up at gamma radiation, up that end. So the photons get their energy from the electrons change in direction or speed?
Well, the photons emanate from the process of the electron changing direction or speed. I suppose it's reasonable, it sounds intuitive to say that if those electrons did that in a faster way, then probably the photons that they gave rise to
would have the higher energy.
Yeah. And that probably, like, gamma rays only, like the really high energy end of the EM band, they only emanate from extremely energetic, like explosions, the biggest explosions you can imagine out in space. So yeah, it's probably true to say that the more vigorous the acceleration or change of direction the electron took, then the higher energy the photons,
wow.
and the higher frequency just then as well. Now, next week we are obviously going to dive into the wonderful individual things that are in the I nearly said it again, the EM spectrum.
The EM spectrum, yes.
And but let's just briefly list what they are. Now, as you mentioned earlier, we slice it up into these different bands for our own human convenience. It's actually one smoothly rising,
continuum.
Excellent. Good.
There you
word.
go. Yeah.
Good
I'm just proving I'm listening.
Good work.
I'm not just sitting here with my eyes closed.
So at the lowest level, radio waves. We use them for carrying information. They carry voice, they carry data, they carry GPS signals, they carry all kinds of interesting stuff. Anyway, they're the longest wavelengths, could be kilometers, some of them in length. Next up is microwaves.
I'd say this is the longest wavelength most people have listened to.
Would you
we go on for days.
I feel our one listener is probably soundly asleep now and probably on his third session of REM sleep.
Mammy, you can turn us off now.
Microwaves.
Nice segue.
I'm known for my subtlety, if nothing else. Right, famous for heating water. Also, actually, they are used as radio waves for certain specific applications, like links between communications masts, that kind of thing. But yeah,
wait a minute. Microwaves are used as radio waves.
Yeah, so they're only slightly up the spectrum from radio. So their properties are kind of similar in some ways to radio waves, so they can be used to carry information as well, and it suits certain applications to use microwaves. And actually, some of the newer Wi-Fi standards use microwave frequencies instead of what we would traditionally call radio frequencies.
But they're not going to find out, like, in 20 years or 50 years, like cigarettes, they're like, we're actually slowly cooking ourselves in our house
the people who insist on sitting on their Wi-Fi router probably are in trouble, all right.
I don't know who those people are. I don't know who you've been hanging around with.
Those antennas can do terrible damage.
Next week on Scientific Euphemisms, Senan will be, I don't know what he'd be talking about, but I won't be here.
And it certainly won't be the BBC. Anyway, next one up is infrared, which we already discussed is heat. Or at least the heat that we feel emanating from objects. However, it is also extremely useful for astronomy, and we'll get into that next week. Next up from infrared is visible light. And this is what we can see. And it's also the spectrum that plants use for photosynthesis to take the energy from sunlight and turn it into something chemically useful in the body of the plant. The weird thing about visible light is it's actually less than 1/100% of the entire EM spectrum is the visible part that we can see. So we're only sensitive to the tiniest fraction of EM radiation. Next up from there is ultraviolet. So that's like, you can think of that as very high energy light. It's produced by the sun, amongst other things. And there's a few different flavors of ultraviolet, and some of the more energetic flavors are kind of dangerous. Then now we're getting into the really crazy stuff. X-rays. Those can pass right through our body and take pictures of what we look on the inside. I'm reminded of that Turning Japanese. Remember that one hit wonder, the band The Vapors?
I didn't remember the name. But I remember the song. Yeah,
there was a line in the song. So this song is kind of a love song or a song of adoration to his girlfriend. And there's a line in the song where he said he's going to ask the doctor to take a picture so he can look at her inside as well.
Right.
So yeah,
Okay.
I'm not surprised they were a one-hit wonder.
Yeah, absolutely. They should actually be put away. Stuff like that.
And finally, at the very top end of gamma rays, which is the complete Looney Tunes stuff, the amount of energy that they have at their disposal.
So they're all like, the higher the energy, the more dangerous they are.
Oh, totally, yeah, because those photons will hit things, us or object or other things, and if they have enough energy, they will cause changes in our cells.
Aha, gamma rays. I knew I'd seen them before. Dr. David Banner.
Oh, the green guy.
Yeah, absolutely. The Hulk, I believe he was known
The
as.
Hulk, yes, the Hulk, yeah.
Yeah.
He was extremely fortunate that all that the gamma rays did to him was turn him green and large, because they could have turned him into a little mucky puddle.
And do we use gamma rays, Ran?
Well, scientists use them to measure things that are going on in the universe, very energetic things.
Okay. So but not anything practical of a sort of.
I think gamma rays are used as part of radiation therapy for cancer.
Oh, okay.
Wow. So there was I remember there was one technique, I don't know if it's still in use, called gamma knife, where they were able to direct narrow. It's like, the way a laser beam is like a really narrow beam of light. Well, I think they were able to do something similar with gamma, where they could direct a thin stream of gamma rays from several different directions at the same time to converge on the tumor.
Okay.
So it was only where they converged that their effect was strongest.
Yes. So they weren't killing everything all around it.
Yeah,
it was just...
yeah. So look, I haven't heard that term in a long time, so I don't know if that's still in use, but probably there's some version of it is still in use. And we've been talking now for half an hour. I think maybe this is a good place to draw a line under the first part of this episode.
To wave goodbye.
Yeah.
Wave goodbye to our friends.
You've been waiting the whole day to say that, haven't you?
So long.
And,
but my head is full now. I don't know about our listeners, but my head is definitely full. And I'm still back with the particle wave thing. That's my Waterloo, I think.
Yeah, it's pretty mind-bending, all right. And we didn't even get as far as talking about the speed of light, which is another mind-bending thing.
Oh, good.
But we'll open next week's episode with that before we dive into the details of the individual ones.
Okay, well, come back next week for more electromagnetic wave-related fun and frolics with Senan and Joe here on Enough with the Science.
I bet you can't wait. I'm Senan, and this is me signing off.
Okay, I'm Joe. Take it easy.